Hello everyone. Today let's look at the principles and the methods for planning IPv6 addresses. An IPv6 address has 128 bits. The leftmost 64 bits make up the network prefix, which can be further divided into fixed prefix and the subnet prefix. A fixed prefix is equivalent to a globally routing prefix, which is requested from an address assignment organization. This means that such a prefix cannot be planned by an enterprise. In contrast, a subnet prefix can be planned. The remaining 64 bits make up the interface ID, which identifies globally unique link interfaces. An enterprise can plan the subnet prefix and interface ID parts. Let's look at some basic principles in planning IPv6 addresses next. First principle is uniformity. All IPv6 addresses, whether they are network, user, or platform addresses, must be planned in a unified manner. The second is semantics. IPv6 addresses must be attached with semantic meanings. As type belong network and the administrative region. This facilitates address tracing, network management, and traffic control. The third is readability, meaning that IPv6 addresses must be easy to read. Because IPv6 addresses are written in hex notation, it can be difficult for us to read and use. To help get around this, it's best to plan addresses separately with 4 bits as a group. In this way, we can easily identify any changed part or part that needs to be encoded. In addition, addresses planned like this are also simple in expression. Fourth, uniqueness. IPv6 addresses include globe unicast addresses, unique local addresses, and link local addresses. A globe unicast address is globally unified. A unique local address is equivalent to a private IPv4 address. A link local address is also globally unique, but used only by the local link. Considering that the IPv6 address space contains sufficient addresses, we recommend using global unicast addresses for planning, because it is inconvenient to ping or access a link local address from an external network. This, however, is not a fixed rule. Enterprises can choose address type based on their real-world situations. For example, enterprises can select global unicast addresses to access the internet while selecting unique local addresses for their internal production services. Fifth, classification. Addresses must be categorized first by purpose, then type, and lastly region. Categorizing them by purpose means that network, user, and platform addresses need to be planned separately to facilitate independent aggregation and advertisement of addresses. For example, on the network shown in this figure, service addresses on the network can be advertised after being aggregated. And the policies can also be applied to limit the traffic from external networks to visit the addresses on this network. The latter improves network security. The main reason for categorizing them by type is because different types of addresses require varied advertisement scopes. For example, SRv6 locator addresses need to be advertised throughout the network for E2E SRv6 BE forwarding. Loopback addresses may only need to be advertised to their own NMSs. Link interface addresses may need to be advertised to other hosts in their own HTTP areas. Categorizing them by region is mainly for the purpose of management. Since an upper-level organization needs to manage the addresses of its lower-level organizations, addresses allocated by region can isolate different regions. 6. Hierarchical aggregation. Route aggregation is a core capability of IPv6. As such, addresses must be hierarchical and aggregatable when being planned. An aggregated route can be advertised in a routing area on the entire network. In this way, devices only need to learn the aggregate route rather than all specific routes throughout the network. This exponentially reduces the number of routes to be learned, simplify the network. Another benefit is that routing policies and the traffic control can be implemented across different networks. Furthermore, if route flapping or another fault occurs in one IGP area, this fault is effectively isolated from other IGP areas. This figure shows an example of hierarchical address planning. The backbone network and the metro network are each allocated with independent area space. On the metro network, aggregation and access devices are further allocated with an independent address space through the aggregation and access networks, respectively. 7th, easy to use. We should take future service application into account when planning addresses. For example, SRHs that contains SRv6 locator addresses need to be extrapolated during SRv6 TE tunnel forwarding, increasing the payload of service packets. This makes forwarding less efficient. Therefore, SRHs need to be compressed. During address planning, compressible parts should be grouped together to facilitate compression. Taking another example, future services may require deterministic SLA assurance. A network needs to be sliced to meet this requirement. When addresses in different slices need to be aggregated, sliced ID need to be put in place during address planning. 8th, security. During addresses planning, source trace information needs to be added to addresses to facilitate future address tracing. In addition, some traffic filtering scenarios also need to be considered during address planning for the sake of security. 9th, extensibility. Considering that services and the user growing continuously, we must reserve sufficient space to prevent address from being fragmented, as this affects address aggregation and management. The last principle for address planning is to comply with national and industry standards. For example, for Chinese carriers, their address classification and coding must comply with the standards of China's communication industry. Enterprises can choose some of these principles to meet their needs, or add new principles based on their own service features. That's all for this video on the basic principles for IPv6 address planning. Thank you for watching.